My name is Nick DesChamps, and I'm going to be presenting part 2 of a 3-part series on the history of indirect evaporative cooling at Munters DesChamps. And part 2 is on the development of the finite difference program to determine performance of indirect evaporative coolers. We started out in '74 making air-to-air heat exchangers. They were called Z-Ducts. And within a year or two from the time we started, we realized that if we sprayed water or some way or another got the air wet in the exhaust side of the heat exchanger coming from the building space or in the outdoor air itself, we could use the wet bulb temperature to determine performance of the heat exchanger instead of the dry bulb temperature of the exhaust. The figure that's on your screen now is a picture of the very first heat exchangers we made called Z-Ducts, and you can see that we're spraying a mist in there. Unfortunately, the mist only went partially into the plates. Its plates were about 1/4 of an inch or less apart, so when you're spraying and the plates are 36 inches deep or so, it doesn't penetrate very far. So you depend upon the air going through the channels to evaporate the water that's deposited on the plates. Now the second picture is a year later when we started using our Series 79 heat exchangers a couple years later. And we were spraying water into those. So they were larger, but led to issues determining performance, because as you change the configuration of the unit, you have to be able to map what's really going on in that heat exchanger on the wet side plates. We started with this, I just thought I'd show you this, when going back gathering materials for this presentation. I came across a lot of my old works that I spend hours in front of a computer doing. This is the first computer program done for the Z-Ducts. It was done on a calculator that had a strip magnet. That you could do 224 lines of code. So 224 lines of code did not allow you to do a finite difference program. A year or so later, I got my first computer. It was a Hewlett-Packard 85. Some of you probably worked with it, but it allowed you to had enough memory and code capacity where you could actually do a finite difference program. Now I'm going to give you these numbers to let you know what we're up against. A 20 by 20 element, as you know, it's a finite difference, divides your heat exchanger up into a lot of smaller heat exchangers. A 20 by 20 element, that's 400 little heat exchangers, took 23,460 seconds, or 6.52 hours to make a run. So we developed it, and it worked fine. It just, you had to do it before you went to bed at night, and you had the answer when you got up in the morning. Now, a 200 by 200 element takes 0.2 seconds. That's let's see, 400 over 40,000 is 100 times more heat exchangers, and infinitely small amount of time. So we've worked on it for a good while, but what we ended up with in this figure is we could print out all the temperature changes on the dry side of the indirect evaporative cooler and the wet side, and any other characteristic in that element, which allowed us to determine water temperature as the water flowed through the heat exchangers, the moisture content, the performance ended up, we could nail it right on the head. And here's a picture of the newer heat exchangers that we came up with that have been discussed in the other 2 parts of this 3-part series. But we now have a plastic polymer tube, I should say PVC tubes, where the water flows over the outside of the tubes and the dry air goes through the inside of the tubes in a horizontal manner. And here's what is actually taking place in that tube. You have air on the inside of the tube transferring heat into the tube wall itself. And then on the wet side, you have a water layer on the outside of the tubes that range between 1 and 2 mils thick. And that water runs down the outside of the tubes and is evaporated into the scavenger airstream. So you have heat transfer from the hot air or dry air going into the tube, and then if there's water on the tube, you have that heat transfer into the water. If there's no water on the tube, then it goes right into the scavenger airstream. And on the wet side, you have heat transfer from the wet airstream into the water, and you have mass transfer from the water into the wet airstream. So there's a lot going on there. And it's amazing, but the water flowing down the wall is at a lower temperature than either the hot airstream or the scavenger wet airstream. Here's a picture of the element itself with an indication of how the heat flow into that water element is. It goes in from the dry air, like I said. Heat goes in from the wet air, but it loses energy. That water element loses energy when moisture is evaporated into the scavenger airstream. And finally, this will indicate what's going on. The blue line is the dry airstream that's cooling down as it goes through the tubes. The red line is the scavenger airstream picking up moisture but cooling down at the same time. And the green line is the water temperature as it flows down the exit side of the heat exchanger. Now here you see that the water temperature is below either airstream temperature. So it's the water temperature flowing over the tubes that actually cool the dry airstream. And that's sort of amazing that the water is below either airstream temperature, but that's due to evaporative cooling. So we've worked on this program for probably 35 years, continually improving it, and it now takes into consideration changes in moisture. It can be used as a dry heat exchanger when the moisture on the surface is no longer there. And it can also be used for condensing in the dry airstream. So it does everything in that heat exchanger that you can do. Also, it's good for once through water. If we just run the reiteration process one time, you can determine what the performance will be if you're using city water once through. Otherwise, it equalizes out. It keeps reiterating until the water of the sump temperature equals the spray temperature, of course, because it gets pumped back up to the top. So it's a universal, versatile program that we use on all of our projects. Thank you.